In a previous video, we talked about complex numbers and their relationship to the principle of incommensurability. There, we discussed how we need two dimensions in order to mathematically describe complex numbers. We also talked about how the principle of incommensurability itself can be considered as two-dimensional. For this reason, I argue that complex numbers are an expression of the principle of incommensurability. Now, I realize that there's a lot of math in these videos, and it might scare a few people off, but trust me, the math that I'm teaching you is the only math you will need to know to understand the cosmology I'm proposing. After this video, there will be very little math. The math I'm talking about is the only math you need to know. No more and no less. As long as you can add, subtract, multiply, and divide, then you can do the math. The rest is just notation. These are toys compared to the math of the Standard Model. The math of the Standard Model is a complete and utter mess. If modern physics was a computer program, it would be considered spaghetti code. I'm a computer scientist, and so I know what spaghetti code looks like. When I see spaghetti code, I naturally want to rewrite the program from scratch. I have had to do this many times in my computer science career. So in terms of the Standard Model, I am rewriting the program from scratch. There will be hardly anything similar between the Standard Model and the cosmology I'm proposing. So forget all that. It is not a requirement for understanding my cosmology. You're better off not knowing anything. Albert Einstein once said, "Education is what remains after one has forgotten everything he learned in school." I prefer that your mind be clear of the clutter of the mainstream language, which is messed up. The first thing I did was I switched from procedural spaghetti code programming to object-oriented programming. I refer to this as the fractal paradigm. The fractal paradigm is analogous to object-oriented programming in my cosmology. In the cosmology I'm proposing, the principle of incommensurability can be thought of as the base class. All objects in my program inherit from the principle of incommensurability. So please be patient. While I'm rewriting the program, you need to be rewritten too. If you studied mainstream physics for any length of time, you need to be rewired. In order to understand my cosmology, as Einstein said, you need to forget everything you learned in school. So forget what you know or what you think you know, and let's do some math. Now I know what you're thinking, but Ken Wheeler says nature does not do math. Nature does not do math. Meanwhile, Robert Distinti says math is only a mimic of nature. It is not nature itself. Now this, in my opinion, is actually much closer to the truth. Yes, Mother Nature does not do math, but math can mimic nature. The Mandelbrot set is a great example of math mimicking nature. The image on the left is a zoomed-in sub-region of the Mandelbrot set. On the right is the spiral galaxy NGC 1232. Notice the striking similarity between these two images. Of course, I agree that math doesn't mimic nature perfectly, but in the fractal paradigm, math does seem to mimic nature quite accurately. Here's another example of the Mandelbrot set mimicking nature. You might remember this image from my Mandelbrot set as a quasi-black hole video. The figures on the top are real observable cosmological objects. From left to right, we have the Cartwheel Galaxy, the Stingray Nebula, Cat's Eye Nebula. I can't remember the next one, but the last one, last but not least, is Einstein's Cross. In mainstream cosmology, Einstein's cross is thought to be caused by gravitational lensing. In fact, mainstream cosmologists go as far as saying that Einstein's cross is caused by gravitational lensing, even though there is no way to verify this nor prove it. This is an assumption. This is a theory. This is not knowledge. They can't possibly know for a fact that Einstein's cross is caused by gravitational lensing. At best, it is an educated guess. Anyone that claims to know that Einstein's cross is caused by gravitational lensing is fooling themselves. Standard cosmology has many causes. Some observations are blamed on relativity. Others are blamed on quantum mechanics. For example, when asked the question, what is magnetism? Some will say that magnetism is a relativistic effect. Others will say that quantum mechanics is the cause of magnetism. But what if it is neither? Mainstream physics makes a lot of assumptions. The uncertainty principle is also to blame for many observations. If you want to see what I think of quantum mechanics and the uncertainty principle, then you should read my paper, Planck's Constant and the Nature of Light, which is on ResearchGate. Gravitational lensing, dark matter, dark energy, the strong force, the weak force, gravity and electromagnetism. All of these things have different causes in the standard model of cosmology. That is why the standard model has so many models and so many principles and so many laws and rules, so many rules. That is why the standard model is so messed up. Long story short, math can be used to mimic nature. Fractal geometry is a great example of math mimicking nature. So the statement, nature does not do math, shouldn't be taken so literally. It is a fool's folly to make such a blanket statement. It really depends on what math you're talking about. When you were in grade school, you learned something called arithmetic. This is where you learned how to add, subtract, multiply, and divide. Then in high school, you may have learned more advanced topics such as algebra and calculus. This is what we call mathematics. I agree that nature does not do calculus, and nature does not do algebra, and therefore nature does not do mathematics. I can 100% guarantee you that nature does not do mathematics. But nature can do arithmetic. Nature can add, and nature can multiply. It says so right in the Bible. I believe it was in Genesis. In the beginning was darkness, and God said, "Let there be light." This is the principle of incommensurability. Then, a little later, God said, "Be fruitful and multiply." Get it? Be fruitful and multiply. In arithmetic, and is another word for add. In order to understand nature, you only need to know how to add and multiply. It says so right in the Bible. Subtraction, of course, is addition of the negative, and division is multiplication of a reciprocal. So there you have it. For the record, I'm not a religious person, nor am I promoting any religion. I am merely using "in the beginning" as a teaching tool and for poetic license. In the beginning was darkness, and God said, "Let there be light." In the beginning was silence, and God said, "Let there be sound." I use this as a poetic teaching tool to help teach the principle of incommensurability. If two principles are incommensurate, then they will fit nicely into this statement. Coincidentally, or not, in 1996, I did an art show called "In the Beginning." This was long before I had any idea about the principle of incommensurability. This, however, was the beginning of my fractal cosmology. This was the first time I started thinking about the Mandelbrot set in terms of cosmology. In the beginning, the art show, led to, in the beginning, the teaching tool. It led to the principle of incommensurability and the cosmology that I'm currently developing. So you probably noticed the Buddhist theme to this poster, and there's a reason for this. You likely recognize these images from my previous video. These two images are two incommensurate emanations of the Mandelbrot set. The figure on the left I refer to as Buddhabrot. The one on the right is called Bubblebrot for obvious reasons. Bubblebrot on the right is an emanation of the central black hole region of the Mandelbrot set. The points from this region are used to generate Bubblebrot image. Buddhabrot on the left is an emanation of the outside region or photon sphere of the set. The points from this region are used to generate Buddhabrot. These two images are incommensurate in principle. They have nothing in common other than the fact that they both come from the complex plane, and they are both generated using the same formula, z equals z squared plus c. Without complex numbers and this formula, the Mandelbrot set and these two images would not be possible. Keep in mind that the very little math went into the generation of these images. The math is simple, but the objects are complex. Ken Wheeler uses the term simplex to describe his missing secrets of magnetism. The Mandelbrot set, Buddhabrot and Bubblebrot, are also simplex. They are both simple and they are complex. So, back to the math. Let's recap the connection between complex numbers and the principle of incommensurability. First, we have the real component of the complex number. Remember, in Distinti's-Vortrix algebra, all scalars are two-dimensional, and so the container for the real component of a complex number is a two-dimensional matrix. Here is the imaginary component, which is also two-dimensional, but it is not a scalar. Notice that there is nothing similar between these two matrices. The real component is on the forward diagonal, the imaginary component is on the backward diagonal. In the real component, both entries have the same sense. In this case, they are both positive. They can also be both negative. In the imaginary component, both entries are on the opposite diagonal and they have opposite sense. One is positive and the other is negative. In matrix math, real component is by definition a scalar. The imaginary component is by definition a rotation matrix. Real scales and imaginary rotates. So, both real and imaginary numbers have different jobs. They perform different functions. Now let's put it all together. When you add the real component to the imaginary component, you end up with a complex matrix on the right, which is also a two-dimensional matrix. As you can see, the real and imaginary components can happily coexist in the same matrix without interfering with each other. This is an important point. In general, incommensurate principles can coexist, but do not interfere with each other. Also notice that the real diagonal and the imaginary diagonal are orthogonal to each other. In general, orthogonality is a signature of incommensurability. So that's it for complex numbers for the time being. Next, we're going to do a bit of trigonometry. Yes, nature does not do trig, but we can use trig to mimic nature. As Distinti says, math is merely a mimic for nature. Nature does not do math, but math can mimic nature, albeit imperfectly. Math is an imperfect mimic of nature. As we saw earlier, the Mandelbrot set is a great example of math mimicking nature. In physics, sine and cosine are generally used to mimic oscillating phenomenon in nature. All oscillating phenomenon can be modeled or mimicked using various combinations of these two functions. Nikola Tesla once said, "If you wish to understand the universe, think of energy, frequency, and vibration." In order to model frequency and vibration, you need to do a little math. In order to understand frequency and vibration, you need the principle of incommensurability. As I said earlier, orthogonality is a signature of the principle of incommensurability. It is well known that sine waves and cosine waves are 90 degrees out of phase with each other. This is another way of saying that sine and cosine functions are orthogonal to each other. Orthogonality, of course, is a signature of incommensurability. In other words, sine and cosine can be considered as incommensurate principles. Remember, in the last video I stated that orthogonality is almost always associated with 90 degrees. In this case, the two orthogonal principles are 90 degrees out of phase instead of 90 degrees perpendicular. In other words, 90 degrees out of phase is another kind of orthogonality. Since sine and cosine waves are generally associated with temporal phenomenon, like waves, 90 degrees out of phase can be considered as a kind of temporal orthogonality. As perpendicular 90 degrees is spatial orthogonality, 90 degrees out of phase is temporal orthogonality. This was a huge revelation for me. Now, let's look a little closer at this picture. On the left, we have a helix wave. A helix wave has the geometry of a spring. On the right, you see two orthogonal projections of the helix wave. The sine wave is projected onto the back, and the cosine wave is projected onto the bottom. When you project a three-dimensional helix wave onto two orthogonal planes, as seen in this picture, you get the sine wave at the back and the cosine wave on the bottom. In other words, sine and cosine waves are merely two-dimensional orthogonal projections of a three-dimensional helix wave. The helix wave is the wave that nature makes. Sine and cosine are merely shadows of the helix wave. They are shadows. Sine waves and cosine waves are intimately related to complex numbers by the following formula. This equation, named after Leonhard Euler, is ubiquitous in math, physics, and engineering. Richard Feynman referred to Euler's formula as the most remarkable formula in mathematics. He also referred to it as our jewel. Anyone that is anyone in the scientific community has seen this formula. The theta in this formula refers to an angle, or more appropriately, the phase angle. We normally talk about cosine of angles and sine of angles, so theta is an angle. Also notice that the imaginary identity I also appears in this formula. Everywhere we find the imaginary identity I in physics, we can assume that it has something to do with complex numbers and the principle of incommensurability. So what is Euler's formula? Euler's formula is in fact a mathematical expression of the helix wave. The cosine part of the formula corresponds to the cosine projection of the wave. The sine part of the formula corresponds to the sine projection of the wave. Together, they make the helix wave. There is, however, something missing from this formula. This is a beautiful and elegant formula, but as specified, it is not complete. There is something missing. Something is being hidden. To explain what I mean by this, we need to take a few steps back and talk about imaginary numbers. When you look up imaginary numbers on the internet, you often see something like this. I is equal to the square root of -1. Or you will see I squared equals -1. The identity on the right is correct, of course, but technically the identity on the left is not quite correct. First of all, I want to remind the viewer that all square roots have two solutions. The square root of +1 is +1 and -1. The square root of -1 is +i and -i. +i squared is equal to -1 and -i squared is equal to -1. Therefore, technically, both +i and -i are identities of the imaginary numbers. +i is the identity of the positive imaginary numbers, and -i is the identity of the negative imaginary numbers. So how can both identities be encoded into this one formula? Currently, only the positive imaginary identity is seen in this formula. When you let the square root of -1 itself be the identity of the imaginary numbers, then this encapsulates both the positive imaginary identity and the negative imaginary identity. Now this, of course, doesn't look as pretty as this, but it is technically more complete. So this takes care of the imaginary component of this formula, which is the sine function. What about the real component, or the cosine function? There's nothing written in front of it like the sine function. How come? Well, historically and by convention, it was assumed that 1 was the identity of the real numbers. And for some reason, we made a rule that said, thou shalt never write the identity of the real numbers in a formula. So it never gets written. But now I'm going to show you, using the logic of imaginary numbers, that 1 is not the true identity of the real numbers. If 1 were the true identity of the real numbers, then technically Eulers' formula would look like this. But this doesn't look right. The imaginary identity is a square root, and the real identity is not a square root. This looks a little suspicious to me. Here I argue that we are making the same mistake that we're making with imaginary numbers. The square root of 1 has two solutions, +1 and -1. By analogy with the imaginary numbers, we should be writing Eulers' formula like this. This is the most complete and unambiguous expression of Eulers' formula. It covers both the positive and negative real numbers and positive and negative imaginary numbers. In my opinion, it is not more elegant to hide the identity of the real number in a formula as important as Eulers' formula. Notice that I also put the square root of +1 and the square root of -1 into the exponential term on the left. The left side of this equation is just a short form for the right-hand side, but they both mean the same thing. This is just notation. In my humble opinion, this is how this equation should be written. Everything is written and nothing is hidden. Now we can see the true beauty and symmetry of this famous equation. The orthogonality is now clear. Real numbers and imaginary numbers are orthogonal. The cosine term is the real term, and the sine term is the orthogonal imaginary term. Cosine and sine are incommensurate in principle. Sine is not cosine, and cosine is not sine. Cosine and sine are 90 degrees out of phase with each other. They are orthogonal. They are normal to each other. Thus, they are subject to the principle of incommensurability. For rigor and completeness, you have to write the square root of +1 in the cosine term and in the exponential term. By not writing the real identity into this formula, you might miss the beautiful symmetry of this formula. By not writing the real identity into this formula, you might miss the fact that there is an imaginary component and a real component to this formula. And by not writing the real identity into this formula, you miss a very important point. You miss the fact that the identity of the real numbers is not 1, but is in fact the square root of positive 1. Now this, Richard Feynman, is a jewel of an equation. You won't see this written anywhere in the literature. You're seeing it here for the first time. And for the record, Eric Dollard writes the famous telegraph equation, which has both real and imaginary terms. He explicitly writes the square root of positive 1 in his real term and the square root of negative 1 in his imaginary term. Eric Dollard knows that the identity of the real numbers is the square root of positive 1, and the identity of the imaginary numbers is the square root of negative 1. I also want to point out that the exponential in this formula is an irrational number. E equals 2.71828, etc. Incommensurability is tightly linked with the concept of irrationality. Irrationality and the principle of incommensurability are intimately connected, but that will be the subject of another video. So what does all this have to do with the missing secrets of magnetism? Remember this picture? This is another picture of incommensurability. This is Ken Wheeler's favorite picture. These are the electropotential lines of tension and the magnetokinetic lines of pressure that I talk about in a previous video. As you can see, the electropotential lines of tension in blue and the magnetokinetic lines of pressure in red are 90 degrees orthogonal to each other, and thus, by analogy with the complex numbers, they can and do coexist without interfering with each other. As real and imaginary numbers coexist to form the complex numbers, the electropotential and magnetokinetic lines of force coexist to form the electromagnetic field. This is why complex numbers are found in physics whenever we begin to talk about electromagnetism. This was a huge revelation for me. The principle of incommensurability is surely a unifying principle. This is what the electromagnetic field really looks like. When the potential and kinetic lines of force meet at 90 degrees, the fields are orthogonal and therefore normal. This is the only way it can be. This is the only way these two fields can coexist. These two entities can only coexist when the entities are orthogonal to each other. All of the things you see here are related by the principle of incommensurability. The principle of incommensurability is the base class of all these things. Orthogonality is the key to understanding the principle of incommensurability. In the beginning was orthogonality, and God said, "Let there be loss of orthogonality." So, what is loss of orthogonality? In the cosmology I'm developing, orthogonality is analogous to equilibrium. This is nature's equilibrium. Nature is always striving towards orthogonality. Loss of orthogonality is analogous to loss of equilibrium. When two fields fail to be orthogonal, then they're no longer in equilibrium. When two fields fail to be orthogonal, then they can no longer peacefully coexist. They can coexist, but not peacefully. When orthogonality is set out of balance, then you have loss of orthogonality. So what is loss of orthogonality? So think about it. Orthogonality is normal. Loss of orthogonality is loss of normal. So what is it? Can you guess?